Alright, welcome back. We're on part 2 now of our lecture about pressure. And we've watched this demonstration. We found out that pressure of the air around us is actually surprisingly large. Air pressure is quite strong. In fact, let's try to figure out how strong and how we're going to quantify it and how to measure it and so on. Well, depending on what physics classes you had in high school or maybe even chemistry or something like that, you may have already learned that pressure has a formal definition. Pressure is a force per unit area. It's how much force is being exerted across an area. Well, we like to measure force in America using the English or imperial unit of pounds. We like to measure area using units like square inches. So if we wanted to measure pressure, one unit we could use is pounds per square inch. Pounds is a unit of force. We tend to think of it as a unit of weight. Weight and force are very closely related. And area, square inches, pounds per square inch. That's a perfectly valuable, perfectly fine unit of pressure. And as it happens, if you measure the pressure at the surface of the Earth, it works out to almost exactly 14.7 pounds per square inch. It varies. You're clearly going to learn in this class about high pressure systems and low pressure systems and so on. But 14.7 pounds per square inch is a pretty good average. Now, I didn't bring it. I was going to. I have a 15-pound dumbbell up here. Okay? 15 pounds, pretty close to 14.7 pounds. That is how much pressure there is on every square inch at the surface of the Earth. So, no wonder the can crushed. I mean, 14.7 pounds on every square inch pushing in, of course it crushed the can. And there's 14, you know what else also has a cross-section of about 1 square inch? Your eye. Okay, right now there's about 14.7 pounds of pressure on your eye. Why doesn't your eyeball squish? Well, it's because there's fluids inside the eye that are under pressure too, pushing outward. If you were in the vacuum of space where there wasn't air pressure around you pushing in, your eyes would go and splat, right? Because the pressure of the fluids on the inside of the eye would be greater than the pressure on the outside, and your eye would pop. In the same way, then, in a room, the pressure of the air around you pushing in on your eye is just as much as the pressure on the outside of the inside of the eye pushing out, and therefore your eye doesn't, burst or get crushed or anything like that. 14.7 pounds per square inch is the typical pressure at the surface of the Earth. Pounds per square inch, that's a term you've heard before, or PSI, often abbreviated PSI. Oh yeah, when you measure the pressure in your tires of your car, they're measured in pounds per square inch. Now, just so that we make sure we get this concept clear, when you measure the pressure of your tires, what you actually measure with your pressure gauge is actually the difference between the pressure inside the tire and the pressure outside the tire. So like if your tire is completely flat and your pressure gauge that you have in your glove compartment, and your parents will be very happy with you if you have a pressure gauge in your glove compartment, when your tire is flat, the pressure gauge says 0. That doesn't mean that there's no air in the tire or that the air in the tire has no pressure. It means that there's no difference between the pressure on the inside of the tire and on the outside of the tire. And so, like for example, if you measured the tire pressure and it says 35 psi, what that really means is the pressure on the inside of your tire is 35 pounds per square inch greater than the pressure on the outside of the tire. I mean, if you actually were measuring the pressure inside the tire, it would therefore be 14.7 pounds per square inch plus 35 pounds per square inch, which works out to, what do I have here, 49.7 pounds per square inch. Okay? That's just so that we're clear about what pressure gauge is actually measuring right there. Okay, in our day-to-day life, pounds per square inch is a unit that works well. My 7-year-old son the other day was at a Boy Scouts event where they were launching bottle rockets using rockets made out of bottles, and they filled them up with air pressure from an air compressor, and they had to inflate their bottle to 40 pounds per square inch. And my very inquisitive 7-year-old, not 77, wanted to know what that meant and so on, and it was a big, complicated discussion. But you know what? Meteorologists don't tend to use the unit of pounds per square inch. For various reasons, that's not a unit. That's a good unit for like an air compressor you bought at Sears. But it's not a good way of describing like meteorological differences in pressure from one location to another or one weather pattern to another. Generally speaking, if you watch the Weather Channel and you listen when they have the local every 10 minutes when they have the local weather and so on, they don't generally tell you the pressure in pounds per square inch. They tend to use this strange unit called inches of mercury, which is typically, since the chemical symbol for mercury is Hg, for reasons I can't remember right now, and the symbol for inches is 2 tick marks, they tend to use the symbol tick tick Hg like they have right there. They measure pressure and they describe it in terms of inches of mercury. What in the world, what is an inches of mercury? This is mercury as in the liquid metal, and it comes to us from the idea of how a mercury barometer works. A barometer is an instrument that measures air pressure. Baro is a Greek prefix that means something like weight. Actually, I don't know if it's Greek or Latin. So it's something that measures the weight of, well, in this case it's measuring the weight of the air, which we said was our second way of remembering how to describe air pressure, but we're not there yet. A mercury barometer, then, is an instrument that measures pressure using liquid mercury. Now, it's a little hard from a slide like this to explain how it works. Creighton used to have a nice liquid mercury barometer sitting on the 5th floor of the Hicks and Lead building, but I think they took it down. But basically, it's a little pan of liquid mercury with it kind of looks like a tube or a straw sitting in it. Now, air has molecules that are pushing against the pan of liquid mercury, and that exerts a pressure, and that pushes the mercury up the tube. The higher the pressure of the air, the farther up the tube it can push the liquid mercury. Under typical conditions at the surface of the Earth, the air pressure around the mercury barometer can push the liquid mercury about 30 inches up the tube. In fact, the long-term average is 29.92 inches. Therefore, how high that column of mercury is up the tube turns out to be a very accurate and precise way to measure the air pressure. So 14.7 pounds per square inch, which is the typical pressure at the surface of the Earth, works out to exactly 29.92 inches of mercury. When the pressure around the barometer is higher and the molecules are hitting that puddle of mercury that's in the pan harder, it pushes the mercury farther up the tube, and you have a higher column of mercury. Why mercury? Mercury is a very dense liquid. It weighs many, many times more per cup or whatever than water does. So the air pressure, the 14.7 pounds per square inch, can only push the liquid mercury up about 30 inches up the column. But you could have used other liquids. Torricelli, a famous Italian scientist during the Enlightenment or something like that, famously made a barometer out of wine. His column of wine, though, because wine is much less dense than mercury, was 30-some feet tall. Okay? You could make a barometer out of water. They would be like 27 feet tall or something like that. The problem is the air pressure can push the liquids up the tube too far. How are you going to carry around a 27-foot tall glass column of wine or of water or something like that? Plus, what if it freezes and so on? Mercury is pretty ideal for all these things. That being said, mercury is a wildly dangerous material. Okay? Even ingesting a small amount of mercury or breathing a small amount of mercury vapors can be deadly. And so as a consequence, we used to, in atmospheric sciences at Creighton, have a mercury barometer on display, but the truth of the matter is from time to time it got broken because somebody bumped into it, and then you have to have the guys in the paper suits come from hazmat and clean it all up. It's actually cool how they clean it up. They use magnets to draw the liquid mercury to them and so on. But you can't clean it up yourself or anything like that. It's very dangerous material. Alright, so because mercury barometers are such delicate, fragile things, that's not really an ideal way to actually try to measure pressure. You know, especially when we get to when we start talking about more instruments like weather balloons. When it comes time to launch a weather balloon and we're going to want to know the pressure at some remote location as the balloon flies away, we really don't want to have one of the world's deadliest materials hanging, in a liquid in there. We're going to want a simpler piece of equipment and a safer piece of equipment to measure the pressure. And the kind of tool for the job that we like are aneroid barometers. Now, again, it's a type of barometer, which means that it measures the pressure. Aneroid. Aneroid is a strange word that means something like dry, okay? It's a strange history and etymology to that word. But it's a much more robust and reliable piece of equipment that doesn't have chemicals and stuff like that involved. And basically what it is, if you look at this diagram here that says sealed aneroid cell, think of that as like a little accordion, okay? And it's just sealed up there. When the pressure around it is higher, that little accordion cell can crush a little bit as the air pressure crushes it. When the pressure around the aneroid barometer is less, the sealed aneroid cell, the little accordion in there, stretches out. And then you can see how it's actually kind of rigged up to like a lever and a needle to measure the pressure. That's a very reliable way to measure pressure. You know, these kind of aneroid barometers can be made for pennies. Some cell phones actually have small aneroid barometers in them. You know, any kind of weather balloon, anything like that. My grandparents and possibly yours had a aneroid barometer mounted in their kitchen that tells them the pressure. I don't know what well, we're going to find out that there's a connection between higher pressure in fair weather and lower pressure in stormy weather. But my grandparents were just weather nerds. They liked having a barometer in their house. Those things were all just aneroid barometers. They're cheap, they're reliable, they don't break very much, they're not made of toxic chemicals, etc. You can calibrate it then to tell you when the needle is this far, that's this many pounds per square inch, or it's this many inches of mercury. Pounds per square inch. The scientist in me, oh, I'm having chest pains just listening to pounds per square inch. Inches of mercury. Oh, inches, you gotta be kidding. We need a metric way of measuring this. Scientists hate the imperial system. We need a metric unit of pressure. And going back to our recollection that pressure was a force per unit area, well, as it happens, the metric system provides us with a unit of force and a unit of area. The metric unit of force is called a Newton. Depending on what physics and science classes you had in high school, you may be familiar with the idea of a Newton. It's just a unit of force. And the metric unit of area turns out to be a square meter. Therefore, a metric unit for pressure would be force per unit area, or newtons per square meter. And that's such a useful unit that the people who, the scientific community has given that unit a name. That's called a Pascal. It is in fact named after Blaise Pascal, as in Pascal's wager and things like that. Pascal is 1 Pascal is 1 Newton per square meter. So a Pascal is which is abbreviated PA by the way, 1 Pascal is a Newton per square meter. But here's the deal, a Newton is actually a really small unit of force. And a square meter is a pretty darn big area compared to a square inch. So Pascals are really small. In fact, 14.7 pounds per square inch, our typical pressure at the surface of the Earth, which we learned was equal to 29.92 inches of mercury, is a whopping 101,325 pascals. That's a lot. That's a big number. Each pascal is pretty darn small. Well, pascals then turn out to be a really useful metric way to measure the pressure, or quantify the pressure, describe the pressure. And it turns out that, in equations, and we'll be seeing an equation in a little bit, pascals turn out to be the right tool for the job for that, but you know what? These are just really big numbers. I mean, when a weatherman wants to write down on a weather map what the pressure is at different locations, and he's got to write out 101,320, it's too big of a number. It's too many digits. We don't need something like that. Meteorologists then have a shorthand way of working with pascals. Instead of writing them all out to 6 digits like that, we divide by 100, and we define a new unit called a millibar. A millibar is 100 pascals. So, instead of it being 101,325 pascals at the surface of the Earth, the average pressure at the surface of the Earth is just 1,013 millibars. Don't get bogged down as to well, why is it milli and why is it bar? There's a whole long complicated story as to how that came to pass. Millibars, 1,013. Okay, but that's not such a big bad number. And just to give you a sense here as to, meteorologically, how big of a range are we talking about then? So typical pressures near the surface of the Earth are about 1,000 millibars, 1,000, 1,013, something like that. You probably know that sometimes on the weather map there's areas of high pressure. We're going to be learning all about high pressure systems and low pressure systems and so on. But when you know about an area of high pressure, just to give you a sense, a typical area of high pressure is maybe 1,030 millibars, and a typical area of low pressure would be about 980 millibars, something like that, just to kind of give you a sense of the range, okay? just to give you a sense, like a really, really strong hurricane, which is a very strong area of low pressure, might have a pressure of about 880 millibars. Contrary to what you see on those kinds of shows on the Discovery Channel or in the movie Twister or something like that, we don't actually have good measurements of the pressure inside of a tornado, but based on theoretical calculations, we know it's got to be right around 700 millibars. Tornadoes are very strong areas of low pressure in their center. So just kind of giving you a sense of the range of these numbers, okay? Okay, so we have all these different ways of quantifying the pressure, and we can use them then to depict the weather. Like here I just happen to have a weather map that's actually kind of a mess here, but this is an area of high pressure centered over Minnesota, and it has pressure of a little, what has it got, about maybe 1,035 millibars or something like that in its center. And then there's lower pressure, like if you go off to the west coast or something like that, you can see it's more like 1,010 millibars or something like that. Just to give you a sense, though, that we have this big area of high pressure. That orange and red area on there is an area of high pressure. We're going to later learn the word anticyclone. That's an anticyclone. Oh, and it's going to be associated with fair weather and so on, and you get a sense of the size of it. Okay, it spans many states. Here's a more recent one here. Again, I just did it because this blue area on here is an area of low pressure. I think the center of that low pressure system north of the Great Lakes there is about 990 millibars or something like that. And again, I wanted you to get a sense of the size of it. That bluish and purplish area then spans from Minnesota and Wisconsin over towards Maine. It spans several states when we're talking about an area of low pressure. All right. Now, before we move on to part 3 of the lecture, and we're going to start learning more about these different ways of describing pressure, let's do two or three more questions here. Here's question 4. Typical pressure at the surface of the Earth is about 1,013 blank. Pascals, pounds per square inch, millibars, or inches of mercury. Which one is the one that it's right around 1,000? Make a choice from those 4 options and get a little feedback before you move on to question 5.